days, and you will see this is very, very stable. This is secure. This is environmentally friendly, and it's cheap.
But there are a couple of problems. One, not everyone lives on top of a volcano. Unlike wind and solar installations, which can be built almost anywhere, geothermal plants can only be built on geological hotspots that exist on less than 10% of the planet.
I think Iceland is unique because it has a significant amount of easily found and verified geothermal resources.
And secondly, even in hotspots like Iceland, engineers must deal with the most daunting technical challenge facing geothermal: drilling. That's because all successful geothermal ventures require three vital elements: hot rock, water, and close proximity to the resource. One such venture had all three and was riding high. But they found out the hard way, like its dirty cousin oil, geothermal's resources don't last forever. Hidden in the mountains of Northern California, almost 120 kilometers north of San Francisco, lies the geysers, one of the largest geothermal resources in the world. What looks like a stunning nature preserve is really a 48 square kilometer complex of power plants, the largest and most powerful ever built. Here, 22 individual plants, owned by several separate power companies, generate nearly 3 times more power than all of Iceland's geothermal plants combined. Like Iceland, the geysers sit on top of a rare geological area riddled with California's famous fault lines. Here, massive amounts of heat rise to the surface where they are accessible to drilling. Most importantly, the geysers are filled with underground moisture.
What we have here is one of the thermal areas at the geysers. We have hot springs, and we have fumaroles. We have ground that's very hot to the touch. Until they drilled deep, they really had no idea that there was this huge reservoir below.
But unlike Iceland, where hot water comes out of geothermal wells, the geysers produce steam. The geysers now have over 300 wells. When the steam comes up through the pipes, a complex process turns it from raw power into electricity. First, the steam enters the plant through giant insulated tubes, then down through the floor.
It goes through a steam strainer. We make sure there's nothing that can harm the turbine. It comes down and heads towards the turbine. The steam comes in on 2 sides, and it expands through a set of rotating and stationary blades, extracting all the energy out of the steam.
The steam spins the turbine at 3,000 RPM, turning a giant generator and producing electricity ready to be dispersed to the masses through power lines. When the steam exits the turbine, it turns back into water and is sent to a huge cooling tower.
You do see plumes coming off of the cooling tower, and many people oftentimes think that is smoke, but it's not. What that is water vapor.
It wasn't until the 1970s that the oil crisis persuaded several public and private utilities to try geothermal, then a rarely used technology. At their peak in the 1980s, the geysers had 23 plants generating nearly 2,100 megawatts. More electricity than any other geothermal field in the world, and the equivalent of 2 nuclear power plants. Enough power to light up nearby San Francisco. The geysers had it all: hot rock, water, and easy access near the surface. Then, in the mid-1980s, an unforeseen problem crippled the entire operation. steam from hundreds of wells began to dry up.
They didn't realize that it was an inexhaustible supply of water. Common sense would tell you now that they should have realized that, but...
Where was the water going? Each day, steam was condensed into millions of liters of water and passed through the cooling towers. Some went back into the ground, but 80% simply evaporated into thin air. Within 10 years, the massive loss of water and steam caused power output to drop by over 40%, threatening the plants financially. Outside observers were not surprised by the turn of events.
It in fact was what everyone really expected in terms of a geothermal resource field, which is that the hot water dries up. There is a risk of depleting the resource.
The water reserve that had accumulated over thousands of years was being sucked dry without enough time to naturally replace it. The companies at the geysers suddenly had a problem that green technologies like wind and solar never encounter: an exhaustible resource.
They all basically decided to exit the geysers around the same time.
Everyone except one enterprising company that decided to buy up these declining facilities. By 1999, a power company called Calpine Corporation had purchased 19 of the 22 failing plants, to the surprise of many skeptics. But they had an ingenious plan to bring the wells back to life, something impossible in an oil well. The rock below was still hot. All they needed to do was add water into the empty reservoirs from an outside source to create more steam. How much water? A whopping 72 million liters a day, enough to fill 28 Olympic swimming pools. To solve the problem, Calpine diverted recycled water from nearby counties. Once treated, it travels over 100 kilometers of pipeline to the geysers, where it is injected into the wells, returning to the surface as steam. The plan stopped the geysers' decline, but output today is down more than 50% since its peak in the late 1980s. In order to maintain or increase production, geologists and engineers struggle daily to drill new wells. But drilling itself presents formidable obstacles to the geothermal industry. At one of the geyser's most remote sites, Calpine engineers are drilling a 3-kilometer well in the side of a mountain. Unlike oil and gas rigs, which drill through more porous, cooler rock, geothermal is looking for pure, hard rock, deeper in the ground where the heat is.
In most drilling projects, you don't want fractures because you lose all the fluid that you're putting down the well to drill the well. Well, in geothermal, we're looking for fractures. So we're looking for the difficult places to drill.
At these depths, drilling equipment is buffeted by nearly impenetrable rock, high pressure, and extreme temperatures. The most common and expensive casualty? Drill bits.
This is an 8.5 drill bit. It's typically the size that we drill a production hole with, and we actually push it down as we're rotating to cut the rock. It's a simple thing. It just grinds up rock and makes hole.
Bits, which cost as much as $30,000 each, typically break down every 40 hours on a job that usually takes about 4 months to complete. On a typical well, that can cost nearly $360,000 just in drill bits.
When we drill through this plug, we'll come out of the hole and complete the well.
Suddenly, they're back in business. A few hours later, readings coming from sensors attached to the end of the drill bit indicate a large temperature spike. They could hit an explosion of steam at any minute.
Steam will come. Green energy.
For drillers, that's what it's all about. From small